find angular velocity. So as a circular object rotates counterclockwise about its center, an object at the edge moves through an angle relative to its starting position, known as the angular displacement, or the angle of rotation. Determine the angular displacement in radians of 4.5 revolutions. Round to the nearest tenth. So 4.5 revolutions. We can do this dimensional analysis style. 1 revolution is 2 pi radians. So, right, 1 full circle is 2 pi radians. So our revolutions cancel, and we get 9 pi radians, or rounded to the nearest tenth, 9 pi is 28.3. Right, so 2 pi radians in a revolution, multiply the number of revolutions by 2 pi. The ratio of the change in the central angle to the time required for the change is the angular velocity. That's the angular displacement divided by time. Angular velocity is usually represented by the lowercase Greek letter omega. So, angular velocity omega is the angular displacement theta divided by time. All right, that's time. Angular displacement. And that's angular velocity. So the angular velocity of 7.3 revolutions in 5 seconds. So 7.3 revolutions in 5 seconds, but we want this in radians per second. So multiply by 2 pi radians in 1 revolution. Revolutions cancel, and we get an answer that's going to be in radians per second, which is what we want. So that's going to be 7.3 times 2 pi over 5, which is 9.2 radians per second. That was a 5, not an S. The Children's Museum in Indianapolis, Indiana, houses an antique carousel. The carousel contains 3 concentric circles of animals. The inner circle of animals is approximately 11 feet from the center, and the outer circle of animals is approximately 20 feet from the center. The carousel makes 2 5/8 rotations per minute. Determine the angular velocity of someone riding an animal in the inner circle and of someone riding an animal in the same row in the outer circle. So, angular velocity, right, 2 5/8 revolutions or rotations in 1 minute, right? 1 minute is 60 seconds, because we're usually going to do our angular velocity in feet per second, or radians per second. Right, so minutes cancel out, and then we need 2 pi radians in 1 revolution. Revolutions cancel out, and we get an answer that's going to be in radians per second. So 2 5/8 times 2 pi over 60 radians per second, which is 2 5/8 times 2 pi over 60 is 0.27 radians per second. And so that's for the angular velocity. And so the angular velocity is not dependent on how far away you are from the center. The angular velocity is just based on the number of revolutions. So both riders, in the one in the inner circle and the one in the outer circle, are going to go through the same number of the same angular velocity. They're traveling at the same angular velocity. They both travel at 0.27 radians per second. So the angular velocity is about how fast an object is spinning, and is not related to the radius or the size of the circle. The linear velocity is how fast you're going if you're on the outside of the circle, and that is going to be related to the radius, right? So again, think of our carousel riders. The one on the inside goes through 2 5/8 revolutions per minute, and each revolution is this distance. The one on the outside goes through the same number of revolutions per minute, but each revolution is much bigger because the circumference of the bigger circle is bigger. So the one on the outside is going to be going faster. So handy thing about radians, if our angular velocity is in radians per second, our linear velocity is, sorry, there should have been R, just the radius times the angular velocity. Radius, or R times theta over t. Right, where theta over t was omega, the angular velocity. So we just take that angular velocity and multiply it by the radius, and that gives us the linear velocity. So linear velocity of the two riders from example 3, their angular velocity was 0.27, and the first rider had a radius of 11 feet, so her linear velocity is going to be 0.27 times 11, which is 2.97, or about 3 feet per second. The second rider is at a radius of 20 feet, so her linear velocity is going to be 0.27 times 20, which is going to be 5.4 feet per second. So the angular velocities are the same, but the linear velocities are dependent on the radii. The tires on a race car have a diameter of 30 inches, and I'm going to go ahead and write that as a radius of 15 inches so that I don't forget that. If the tires are turning at a rate of 2,000 revolutions per minute, determine the race car's speed in miles per hour. So the race car speed is also going to be the linear velocity, which is going to be r theta over t. So theta is 2,000 revolutions in 1 minute. We want the car speed in miles per hour. So let's go ahead and turn these minutes into hours. 60 minutes in 1 hour. So now we've got revolutions per hour. We're going to turn these revolutions into radians by multiplying by 2 pi. So now our revolutions cancel out. We got radians per hour. If we multiply by the radius, which is 15 inches per 1 radian / radius, that gives us inches per hour. And then we need to turn those inches into miles. So we're going to divide by 12 inches in 1 foot. So our radians cancel out. Our inches are going to cancel out. It's going to give us feet per hour. And then 5,280 feet in 1 mile. And our feet cancel out. And now we get an answer in miles per hour. So that's 2,000 times 60 times 2 pi times 15 divided by 1111, 12 times 5,280. You put all that into your calculator. Times 60 times 2 pi times 15. And divide that by 12 times 5,280. And come up with 178.5 miles per hour. Dimensional analysis, it's a fun time. And that's it. Tune in next time for graphing sine and cosine.